Welcome to video 17 on the TTB course. This video is from part 4 of the course. In part 4, we consider techniques for monitoring TT systems. In this video, we consider use of an external watchdog controller in a TT system. This material is based on chapter 17 in the ERES2 book. If you have not yet read chapter 17, I suggest you stop the video now, read the book chapter, and come back and watch the video again. So let's just consider again what we discussed in relation to low-level power-on self-tests. We will typically aim to investigate some or all of the following elements during power-on self-tests on each processor in a TT system. The clock frequency, check that the program counter and other CPU registers are correct, check the RAM, check the ROM and flash memory, and check the interrupt operation. So these are some of the lowest level power-on self-tests that we would carry out. The key question that we're trying to answer through the use of these kind of low-level posts is as follows. Do we have an operational processor to work with? If the answer to these questions, if the result of these checks is to suggest that we don't have an operational processor, then all we can try to do is enter a fail-safe processor state. The challenge that we've discussed in previous videos is obvious. If our platform is based on a single processor, and this processor fails its power-on self-tests, it's difficult to be confident that this processor will be able to perform the operations that are needed in order to fail safely. The design process we're going through is all about confidence. We want to be confident that the system will operate correctly. So if we have only one processor in the platform, and failure of the power-on self-tests could result in a dangerous situation, then we need to consider incorporating something like an external watchdog controller, something we consider in this video, a warrantor unit, something we consider in video 20, and/or we need to consider migrating to a multiprocessor platform such as a duplicator platform, something we discuss in video 21. So in this video, we're going to focus on watchdog controllers, external watchdog controller options, EWDCs. Let's consider a simple example. As part of the control system for an industrial robot, our microcontroller, illustrated on this slide, is responsible for controlling the power supply to a drive. Let's assume this drive is a hardware unit that controls our robot. If power is supplied to this drive, then this robot is capable of moving. So under these circumstances, the drive is on. We assume that's correct, and the system can operate normally. Suppose we suffer electromagnetic interference, or the main microcontroller is subject to an overvoltage situation. We may end up leaving the port pins on the microcontroller in an unknown state. So we may damage the microcontroller and leave the drive enabled, and yet we have no control over the drive state by now. This is a potentially dangerous situation. Let's modify the design a little. Now we add an external watchdog controller to the system. So now the watchdog controller is also responsible for ensuring that the drive circuitry to our robot is enabled. And the watchdog controller is, we assume, controlled by a pulse stream that comes from our microcontroller. If we don't generate a pulse stream from the microcontroller, the watchdog controller is not enabled and will have no power to the drive. So under these circumstances, everything is okay. The microcontroller is operating correctly, it's sending a pulse stream to the EWDC, the drive is powered up and the robot can operate normally. Now, this time we damage the microcontroller again. In these circumstances, the pulse stream to the EWDC is stopped, therefore there's no power to the drive is off, and the robot stops safely. That's a simple procedure that we're trying to support through the use of an external watchdog controller. So what can we do with an EWDC? Use of such a component can help to address concerns about the behavior of a platform based on a single processor in which we fail one or more of the power-on self-tests. We raised this problem for the first time in video 13. Use of an external watchdog controller can also be employed as a means of ensuring that the platform outputs remain in a safe state during same mode resets, something we discussed in video 8, and during other mode changes. Use of an EWDC can also increase confidence in our ability to deal safely with an abnormal processor state in a platform based on a single processor at all times during the platform operation. Use of an EWDC can increase confidence in our ability to deal safely with common cause failures in platforms based on multiple processors. The EWDC will usually be based on a COTS watchdog monitoring unit or assembled from discrete hardware components. The communication between the processor and the EWDC will be some form of dynamic signal. That is, a signal that can only be generated by a design with a functioning scheduler. This might, for example, consist of periodic heartbeat messages involving a simple pulse chain. If we do this, these heartbeat messages will be generated by a task. In circumstances where the messages fail to arrive on time, the EWDC is intended to detect this and place the platform outputs into a safe state. This will usually mean removing power from or otherwise rendering safe a system that is being controlled. So we have a very simple system here that is intended to operate only when it receives a dynamic signal from a processor in the system. The EWDC will operate very simply. It will set an output at logic 1 if a pulse stream or other dynamic input arrives as expected. It will set an output at logic 0 otherwise. The EWDC will usually be stateless, that is, it's non-latching. If the pulse stream starts again after a break, the output goes back to logic 1. It doesn't remain at logic 0 because there was a period over which it didn't receive any dynamic outputs. The signals that are used to control the EWDC should always be generated by means of a task or tasks. We want to ensure that the EWDC is only operated when the scheduler is fully operational. Use of an ISR, even the scheduler ISR, would not achieve this. It's possible that the scheduler ISR will continue running while the rest of the scheduler is not operational. How does an EWDC compare with the internal watchdog timer? These are different things. The names are similar, but we use watchdog controller versus watchdog timer to try and help emphasize the difference. The purpose of the EWDC is to control the processor outputs and force these into a safe state in the circumstances where the processor or scheduler is not capable of functioning normally. Unlike an IWDT, the EWDC is not expected to reset or restart the processor. This is very important. We're not expecting to reset or restart the processor by means of the EWDC. If control of a processor is required, we suggest that a warranty unit, something we'll discuss in video 20, is considered as an alternative to an EWDC. So To emphasize again, unlike a watchdog timer, the EWDC is not expected to reset or restart the processor. So here's an example of an off-the-shelf component that might be used to implement an EWDC. This is a MAX 16997 device. So this is our microcontroller. Just to emphasize the fact that the EWDC is not itself a watchdog chip, this design has a separate watchdog component incorporated in it. You may or may not require such a device in your design. It's not an essential component here. But it emphasizes the fact that this is not functioning as a watchdog timer. So here we have we feed a pulse train to our EWDC, and that controls our backup circuitry peripheral in this example. This example is taken from the Maxim datasheet. You might like to take a look at that datasheet if you want to explore this example further. So this is how we might use such a device to implement the design that we discussed a little earlier in this video. We've got our microcontroller, we assume running a TTC scheduler. As a result of one or more tasks in that schedule, we're generating a pulse chain. This is driving our MAX 16997 chip. That's generating an enable output, which we assume is enabling the operation of our robot. So we may have other outputs from this device that control the operation of the robot, but this external watchdog controller is controlling the power supply to the robot, we assume. In all designs, we need to consider the possibility of common cause failures, CCFs. Suppose, for example, we've got a platform based on a single processor plus an EWDC. In many cases, the processor and EWDC are likely to be in close proximity to one another, probably on the same PCB, or at least in the same box. In this case, we need to consider scenarios in which both the processor and EWDC can be damaged by the same event. For example, an excessive power supply voltage could leave both the processor and EWDC in a dangerous state. The use of discrete components, for example MOSFETs, may allow us to produce a custom high voltage EWDC that might stand voltages of 100 volts plus. If we use such components, we will still want to ensure that our EWDC is controlled by a pulse stream. MOSFET-based designs that implement a charge pump or bootstrap may provide a starting point. Such hardware designs are beyond the scope of this course, but a few minutes on Google will give you some initial design ideas. So we need to consider common cause failures, such as the possibility that a high power supply voltage could damage the processor and EWDC. Building your own EWDC using discrete components, for example MOSFETs, may allow us to address such concerns. We also need to consider common cause failures in designs that involve more than one processor. Again, a high voltage EWDC is often used in duplicator designs as a means of dealing with common cause failures that may result in damage to both of the processors in the system. I've sometimes been asked whether it's possible to use a small microcontroller to implement an EWDC. We can do this. It's possible to implement an EWDC using a suitable small microcontroller. Let's call that an MCU EWDC. This may make sense if we require only stateless shutdown behavior from the MCU EWDC, and we wish to keep the processor and its monitoring device physically separate, usually because of common cause failures concerns. So for example, if we used a microcontroller to implement our EWDC, we can very easily set up a UART or a CAN based link between the main processor and our microcontroller based EWDC. This can be an effective solution, and low cost, appropriately rated microcontrollers are available. However, if you're going to consider using a microcontroller to implement an EWDC, I suggest you consider use of a warrantor unit instead. We'll discuss warrantor units in video 20. These have a number of advantages over the use of a microcontroller based EWDC, and in most circumstances it typically makes more sense to use a simple hardware based or off-the-shelf components to make an EWDC and then use a warrantor unit in the design if greater control is required. We'll say more about warrantor units in video 20. Any components we use in the system need to be subject to posts and BISTs. So in many cases EWDCs are used to maintain power to a piece of equipment. We want to be confident that the EWDC will be able to remove the power when it's required to do so. The usual way that we test such behavior is by turning off the power very briefly during the system operation, typically for a few milliseconds while the system is operating. The idea is that the switch off will be long enough for us to confirm that power can be removed from the system while being too short to cause any problems for the system being controlled. So periodically we would briefly remove power, disable the EWDC, stop sending pulses to the EWDC to confirm that it will operate correctly. We would do so with very brief switch off periods in order to be able to simply measure that the EWDC and confirm that the EWDC is operating correctly, but we'll make the power off intervals too short to be detectable or to have inappropriate behavior or to cause measurable problems from the system that is being controlled. That brings us to the end of this video. Please read Chapter 18 in the ERES2 book before you continue with the course. Thank you for watching.